In this video, you're going to learn about the linked list data structure, and we'll also go through an example implementation of a linked list in JavaScript. So before we dive into the implementation, let's define what it is. A linked list is a data structure used to represent a list of items. Linked list on the surface seems very similar to an array, which is also used to store a list of items. However, when you look at how the data is organized in computer memory, you see that arrays organize data in contiguous memory cells, whereas linked lists organize data by scattering it across different cells throughout the computer's memory. These are known as nodes. The data is scattered, but it is still connected. Each node consists of two memory cells. One cell holds a value, and the other cell carries an extra piece of data known as a link. The link is what connects each node in a linked list. A link is just the memory address or reference to the next node in the linked list. So if you think about it, a linked list is a data structure that is a collection of nodes that carry a value and a link that points to the next node. It's also important to note that the link for the last node points to null to establish the end of the linked list. Typically, when you're visualizing a linked list, the first node is referred to as the head, and the last node is referred to as the tail. Okay, so let's finally look at an implementation of a linked list in JavaScript. This implementation is available in GitHub, and a link is provided in the description below. A linked list is made up of linked list nodes. So the implementation starts with defining these two classes. First, taking a look at the linked list node class, you have two properties called value and next. The value property is the actual value the node will hold, and the next property represents the link to the next node. When you create a linked list node, you supply a value it should store and optionally provide a reference to the next node. If you don't supply anything for the next property, then it will be set to null by default. Finally, you have a helpful but not mandatory toString method, which you can use to simply get the value currently stored in the node or provide a callback function to the toString method to modify how you want to return the value. Moving on to the linked list class, as you can see, we have the head and the tail properties to represent the first and the last node of a linked list. Also, a compare property, which is really just a utility function to help compare if a value is equal to, greater than, or less than another value. When you create a linked list, initially the head and tail are set to null because there are no nodes in the linked list. So if you want to start adding nodes, you can choose to do so in various ways. For example, you can add a node to the beginning of a linked list, to the end of a linked list, or somewhere in the middle. To add a node to the beginning, you can implement a Prepend method. This method accepts a value that you want to add and uses it to create a new linked list node where the next property of this node points to the current head node. Then you update the head property of the linked list to this new node, because after insertion, it will be the very first node. It's possible to use this method to insert a new node when there are no existing nodes in the linked list. To account for this scenario, you can check if the tail property exists, and if it doesn't, then this node for insertion will be the only node in the linked list. When there is a single node, it is both the head and the tail of a linked list. And finally, the method returns a reference to the this keyword so that operations on the linked list are chainable. You can add a node to the end of a linked list by implementing an append method. First, this method takes the value provided and creates a new linked list node for insertion. Before insertion, the method checks if there are any existing nodes. And if the head of the linked list is not set, then we can assume there are no existing nodes. In this case, the node that gets inserted will be the first node. So both the head and the tail of the linked list is also set to be the new node, and there is nothing else to do, so it just returns. Finally, if the linked list has existing nodes, appending a new node means the current tail node's next property has to now point to the new node. And since the newly inserted node is also the last node, we update the tail property to the new node and then return. Okay, so to wrap up adding a node to a linked list, let's look at the insert method. The idea here is to insert a value at a specific index, but linked list is not index-based as an array, so the method has to incorporate this concept in its implementation. First, It checks if the raw index provided is less than 0. And if it is, then the index will be set to 0, or else the index will be set to the raw index provided. If the index is 0, then technically we can just call the prepend method to do the insertion because the insertion will happen at the head of a linked list. To insert anywhere after the head node, we create a new node, then iterate through the linked list until we get to the specific index where the insertion will occur. If there is a current node at the specific index, then the new node's next property has to point to the current node's next property, and the current node's next property has to point to the new node because the new node now comes after the current node. Finally, if there is no current node, then we check if we're at the tail node, and if we're at the tail node, then the new node has to come after the tail node, making it the new tail node. When the code gets to this point, it just means there are no nodes in the linked list, so the new node inserted just becomes the head and the tail node. Let's finally look at deleting a node from a linked list using the delete method. This method deletes a node that matches the value you provide to it. First, it checks if there are any nodes in the linked list, and if there are no nodes, then there is nothing to delete, so it simply returns null. This section here is focused on the scenario where the node to delete is the head node, and if that's the case, all that is needed is to appoint the node after the head node to be the new head. In this section, the method iterates through the linked list by starting from the head node, and as it iterates, it checks if the node next to the current node needs to be deleted based on a matching value. If it does need to be deleted, then the current node's link is updated to point to the node after the deleted node, which is the next node. The loop breaks if the tail node is deleted or when there are no more nodes to iterate. If the tail node did get deleted, then the tail should be reset to the node before the tail node, which is the current node. There are more methods to explore, but I'm going to conclude this video here and encourage you to go explore the other methods that may be of interest to you. Please like and subscribe, and I'll see you in the next one.